Okay, here we go. Starting section 1.4. Just want to quickly review the two things we've covered so far. One being derivative, which is a rate of change. And what we're doing when we do derivatives, we're actually dividing y by x. Y gets divided by dx. And, and we've done that two ways. We've done it with the 2-point table, and we've done it with the 3-point table. And 3-point table is going to be our default because it's more accurate. Okay, and the second thing we did was definite integral. Definite and here what we're doing is multiplying the y variable by the x variable. And then depending on what those are, if y is velocity and x is time, we know when we multiply we're going to get distance there. But that's not always what we have on those two axes. And we've had one process to do this so far, and the process was counting squares. What we're going to do today is do definite integral again, but a different way. And what we're going to use are trapezoids. So we'll call it the trapezoid rule. So if you find that this exploration sheet, remember we already did the 1.3 notes on the back side, we're going to go through the 1.4. And we'll learn what trapezoid rule, how that works. So here we go. A story problem to start with. We've got Elevator, which is Darth's daughter. Those of you that know Star Wars, Darth Vader, is driving in her rocket ship. At time 0 minutes, she fires her rocket engine. So our time value down here is in minutes. It's always a good idea to keep track of the variables. Or not the variables, but the labels. The ship speeds up for a while, then slows down as Alderaan's gravity takes its effect. The graph of her velocity, which is in miles per minute, is shown below. So we've got velocity here, that's miles per minute. Okay. It says, what mathematical concept would be used to estimate the distance Ella goes between 0 and 8? Well, this is where you've got to kind of think of what we've learned already. If I've got velocity and time, and if I multiply them, that's going to give me the distance. So when I'm multiplying to get distance, that's integral. So this is a definite integral. We'll multiply the velocity by the time to give me distance. So estimate the distance in problem 1 geometrically. So we're only going from 0 to 8, and we only have one way to do this right now, and that's counting squares. And what's going to happen is we're going to take our counting square estimate and compare it to what we get when we actually do it with the new way. So we're going to stop this thing at 8, 5, 6, 7, 8. Okay, if you want to practice this, I would pause the video, go ahead and count and estimate and see how you do. Okay, so go ahead and hit pause, count it up. And then when you turn it back on, I'm going to write my answer down. So I'm not going to use up the video time to do that. Okay. I counted 60.8 squares. And remember, it's not just count squares, it's take the area of the squares. So I have to take how many squares I have and multiply by the area of one square. So 1 square, if I look, I can see they're counting by 1 minute here, so that's a distance of 1. But on the vertical, since that's 100 there, 1, 2, 3, 4, and that's 4, so that's going up by 25. 25, 50, 75, 100. So the area of 1 square is 25, so I'll take 60.8, multiply by 25, and I get about 1,520. My units here Again, we're multiplying. I'll show you what it is. It's miles per minute multiplied by minutes. I'll make that minutes over 1. If I have a fraction, I keep everything in fractions. Cancel the minutes, I can see I've got miles, and that's a distance value. So by counting squares, I estimate that she traveled 1,520 miles in those first 8 minutes. Okay, now they're giving us her velocity equation right here. T cubed minus 21t squared plus 100t plus 110. It says plot this graph on your grapher. Does the graph confirm or refute what Ella figures? Remember, this is what Ella figured it was going to be. So we're just going to take the time to type this into the graph. And you should do this too, because we're going to use the values over here and I'm going to be doing table stuff. So take the time to type this in. Don't just watch. So x cubed minus 21x squared plus 100x plus 110. If I do a zoom 6 on this, I'm probably not going to see much. Doesn't look anything like her graph because I don't have the window set up like hers. Take a look. Her graph is going from 0 to 10, so I'll fix that. And it looks like on the y's, it's going up to 250. So if I went up to 300, I should have a window that looks just like this one here. So go to the window. The x-axis, the smallest time value was 0 to 10. The min was 0, but it went up to almost, well, that's 200, 275. So to match that, I'll put in the 275. And they put a tick mark every 25. Not that this thing matters. You could have left it at 1. It would have just made that y-axis really thick. So now when I graph, it should look very similar to what's on our paper if she was right. And it appears that she is. So tell how you arrive at your conclusion. It matched the calculator. Okay, moving on to number 4. It says divide the region under the graph from t equals 0 to t equals 8, which represents the distance, into 4 vertical strips of equal width. So I'm only going out to 8, so every 2 minutes I'm going to put in a vertical bar. So 0 to 2, 2 to 4, 4 to 6, and then 6 to 8. So there's my 4 regions. Draw 4 trapezoids whose areas approximate the areas of these strips. While trapezoids are just going to stand on end. Remember, trapezoid has 2 parallel sides, which these 2 sides are parallel. Remember the little parallel. Then if I connect this with a straight segment, and here, okay, we typically saw our trapezoids like this, laying on the flat part there. But that definitely is a trapezoid just standing up on its end. Same thing here. That's also a trapezoid. And then there's another one here. And then one here. So I'll call it trapezoid 1, trapezoid 2, trapezoid 3, and trapezoid 4. Okay, by finding the areas of these trapezoids, estimate the distance Ella goes. So instead of counting squares, we're going to actually find the areas of the 4 trapezoids and add them together. So on your notebook paper now, we're going to do that because it's way too much work to try to fit it in this little spot here. So this is going to be, I'll slide this over, number 4 on the exploration. All right, so remembering back to geometry, the formula for the area of a trapezoid, because this is usually what we saw for the area of a trapezoid. You had your 2 parallel sides. Those were the bases, B1, B2, and then we talked the height in between them. And the area of a trapezoid, if you remember, is 1/2 the sum of the bases times by the height. Okay, so we're going to do that 4 times with this thing. My bases are actually these vertical sides because those are the parallel. So to get the length on the bases, I need to know this y value. This base is a little over 100. This base is over 200, over 225. This one's over 225. This base here is pushing 175. We can get these values if we set up our table feature. So let's go to the table. Table set. I've already got the equation in. I want to start at 0 because my first time value is 0. I want that height. But now my increment is every 2 minutes I want the height again. So down here on the, table set, 2. Down here for my increment, 0, ahead of myself there, starting at 0, the increment is 2. Whew. Okay, here we go. Table. So now I know exactly where these values are at. This one is at 110. When it's at 2, it's at 234. When it's at 4, I see 238. When it's at 6, it's at 170. And then at 8, it's at 78. So now I have all the base lengths. Now it's just a little simple plug and chug. And then we're going to come up with a shortcut for this process so it's not quite as painful. So trapezoid 1, using the formula, 1/2. The two bases are 110 and 234. And the height of my trapezoid is how far apart the bases are. Well, my bases are these parallel sides here. They are 2 apart, so my height is 2. Okay, we're not going to work that out because I'm going to show you a little bit of a streamlined version to getting this. Okay, trapezoid 2 is 1/2, 234 and 238. And again, the height's consistent all the way through. It's 2 units apart. Trapezoid 3 is 238 and 170. And then trapezoid 4 is 1/2 times 170 and 78 times 2. Okay. Oops, sorry, didn't get that one on there. If I expand all of this, we're going to be able to see a nice shortcut we can use for this. So we won't have to go through this big process. So what I'm going to do to show it to you, to discover it, is distribute the 1/2. And we'll save the multiply by 2 for at the end. So the first one is 1/2 times 110 plus 1/2 times 234 plus, in the next one, it's 1/2 times 234. Oh, I had a half of 234 plus a half of 234. Think about it, those are just going to add up to 234. Let's keep going. Plus half of 238 plus half times 238. So again, half of 238 and half of 238, that's going to give me 238. Now I'm here, half of 170. Now I'm down here, half of 170 again. And then half of 78. Oh, it almost fit. And then I've got, after I do all of that multiplying and adding, I'm going to multiply by the 2. So, if we take a look at this, I had a half of a 110, and then 110 didn't show up again because it was only a part of that first trapezoid. But here, these are paired up to make a whole 234. These are paired up to make a whole 238. These are paired up to make a whole 170. And then I've got half of that this last one, because this base is only on trapezoid 4. But this one's shared by 2, this one's shared by 2, this one's shared by 2. So our streamlined version of this, the shortcut, so that we won't have to go through all of this and all of this, our shortcut is going to be take half of the first y value, half of the first y value, add all of the middle y values, however many you have. So I'll just say y2 plus y3 plus y4 plus however many you have. In this case, we had 3 of them. And then half of the last y value. Once you do all that, you're going to multiply by the height. Oops, sorry. I do that occasionally. I'm not looking at the screen. So the shortcut is half of the first y value plus the whole second y value plus the whole third y value plus the fourth y value plus half of the last y value. That's y last. And then once you do all that, you multiply by the height and you'll have it. So if I was to start this problem all over, now that I've discovered the shortcut, all I would do is get my table set up like we did. I know I'm going from 0 to 8, and my shortcut is half of the first y value plus all the y values in the middle plus half of the last y value times by the height. And my height is the distance here, 2 apart. So if I was to start this problem all over, what I would want to see on the quiz or the test is going to be that the area equals 1/2 of the first y value is 110 plus the next whole y value is 234 plus 238 plus 170 plus half of the last y value, 78. Do all that times by the height of 2. Okay, so all of the middle ones are added as a whole because I get a half a 1 on one trapezoid plus a half a 1 on the second trapezoid, making a whole one. So if you take the time to crank through that, you will get something I don't have written down. Oh, I do. 1,472. And remember, our units, the units are going to be miles. So if we compare that back to counting squares, we're a little off, but again, counting squares was kind of difficult and nobody can estimate the exact same way, but this technique, we're all going to get the same answer. All right, very good. So there's our new way to do definite integral. It's the trapezoid rule, and we're going to be using the shortcut all of the time. And we'll go through another one in a minute after we finish this sheet up. Okay, we are not doing, 5 just tells you trapezoid rule. We're not going to do anything there. It says use a program. We're going to do that another day. 7 we're not doing. Okay. It says what was the fastest Ella went? Okay, don't get confused by this. Think what fastest is a velocity. What do I know about velocity? Oh, all of these values on the graph are velocities. So what was the fastest Ella went, and at what time was that? I want to know this maximum value up here. Okay, you can estimate it off of the graph, but what I want you to do is learn the feature on the calculator that tells you that maximum. So what I want to show you now is how to find a maximum on the calculator. So back in your notes, a maximum value on a graph. And I'll go slow through this so you can grab your calculator and go through the process. Okay, the first thing you do is you have to have it graphed, which we already do. So graph it. Then you're going to go into this calculate feature here. It's in yellow, so you're going to go second calculate. So let me write these steps down as we're doing it. Second calc. And there's all kinds of things that the calculator will calculate for you. It'll find a value. It'll find a zero, a minimum, a maximum, an intersection, and we'll learn about these later. We're looking for a maximum, so press number 4. Okay, and what it's asking for is the left boundary. What you want to do is slide the cursor over so that you know you're to the left side of the maximum. So just use your arrow to the left till you can see it. It's on the left side there. Okay, I know I'm definitely on the left side of the maximum because it's up here. Once you get to the left boundary, hit enter, and you'll see a little, when you move off of it, there's a little triangle filled in there. Now it's asking you to get a right boundary. What it's doing is you're going to give it a little window to look in, and it will find the biggest value in that window. So now you want to make sure, use your arrow to the right, to make sure you are to the right side of the maximum, hit enter. Now it's saying, well, give me a guess. Get me close to the answer. Let's just slide your cursor up a little bit. Doesn't really matter as long as you're in between your two arrows. Hit enter. And it'll take some time, but it found the maximum. The maximum, the time was 3.04 minutes. The velocity is 248.02 miles per minute. So, we'll be using that quite a bit through the year. So if you need to rewind that and go through those steps again, go ahead, but you'll always have it here to look at. So it says, what was the fastest LON? That's just right off of the graph, and we just showed you that. It was 248 miles per minute. At what time was that? About 3 minutes. Okay, so it's all in keeping track of what's given. This was velocity. Now they're asking for how fast. Know that that's a velocity. Number 9, at approximately what was Ella's rate of change of velocity? We want to know how much the velocity is changing at 5. Well, I can see her velocity at 5. How much is it changing as we pass through there? That's derivative. Okay, so we're going to use our 3-point table. Rate of change, 3-point table. Was she speeding up or slowing down? Remember, the sign on our answer will tell us that, whether it's positive or negative. Okay, so we're going to make a 3-point table. 4.99, try and squeeze it in here. 5, 5.01. So this, I'm going to use the table again instead of the trace. Table set. I want it to start at 4.99, go by 0.01. Reading my values off of the bottom. 210.349399. 210. 209.649401. Okay, I'm going to do the subtracting and dividing right on my calculator because I don't have a lot of room here. Oops. Sorry. So again, I'm going to do the subtracting and dividing right on my calculator. So 210 minus the 210.349399 divide by 0.01. I get a negative 34.9399. Down here, do the same thing. I'll subtract this one minus this one over the change in x. So 209.649401 minus 210. Negative, and then divide by 0.01. Negative 35.0599. Averaging. I'd say it's about negative 35. Okay, units here, I just divided y by x. So the units would be, y is miles per minute divided by minutes. I'll make it minutes over 1. To divide, I got to flip and multiply, so it's going to be miles per minute times by 1 over minute. So I'm going to get miles over minutes squared. And if you take physics, you're going to know that a distance divided by a time squared is acceleration. Because it's negative, it tells me she's slowing down. So at what time does Ella stop? Based on the graph, does she stop abruptly or gradually? Okay, she stops when her velocity is 0. If I go back, I don't know if I can catch it on the graph. She's really close here at the 10, or I can look into the table. And how we get that is just tracing on the graph, or looking into the table to see where it's close. So I think I'm actually going to go with the table. I'll have it start at 10 just to see where it's at. Okay, I can still see it's still slowing down. I'm going to go up to the 11. I'm going to have it go by ones. Oh, I hit it at 11. So at 11 seconds. It asked if it was an abrupt stop or a gradual stop. I think I could see it was kind of slowing down gradually before, but if you want to take a look again, I'll go from 10. I'll go by 0.01 to see how big the, yeah, she's going 10, 9.8, 9, 8, 8, 8. It's slowing down. It's still in the 8s, then the 7s. It's a nice gradual slow down here. 5, 4, oh yeah, nice gradual slowdown. Otherwise those numbers would be jumping by a lot if it was an abrupt stop. Okay, what else do I have? Oh, I just want to practice one more time with that new trapezoid rule. So, this one's right out of the book, otherwise I would have assigned it for homework, so it's kind of nice getting one of the homework problems done. It's number 2 in the book. I'll just call it example 1. I'll show you the problem. You don't need your book. It says, pace walker enters a walkathon. She starts off at 4 miles per hour, speeds up as she warms up, then slows down again as she gets tired. She estimates that her speed is given by, here's her velocity, where t is the number of hours since she started, and v is in miles per hour. Okay. It says pace walks for a total of 3 hours. Draw the graph of velocity as a function of time for these 3 hours. Sketch the result on your paper. So we're going to let the calculator make the sketch for us. So, calculator right here. Clear. We've got her velocity is, I got to check my mode on this one. I'm good. 4 sine 1.4x. Okay, window. Okay, the time was only for 3 hours, so 0 to 3. Y is her velocity, and she's only starts off at 4. She speeds up some. Think about walking. There's no way she's going to get up 275 miles an hour walking, so I'm going to max that out at about, I'm just going to say 8 and see. It's just a guess, using some common sense. If it's not big enough, or I'll go back and change it. Okay, it's definitely big enough I can see the top of the graph. Okay, so it's just kind of it's one of the sine humps. Okay, our units, you should always keep track of the units. T is the number of hours, and then miles per hour. Okay, so A is done. It says, tell Y a definite integral would be used to find the distance she has gone. So this was A. B, I can use an integral because I know that distance is velocity multiplied by time. Rate times time. And that's what I've got. I want to multiply my two variables together. Anytime I do y times x, I'm doing the definite integral. And it's giving me the area under the curve. Okay, estimate the integral using 6 trapezoids. So I want to divide this thing up into 6 equal pieces. So 1, 2, 3. 1, 2, 3, 4, 5, 6. Okay, I'm going to let the calculator give me all of these y values. So think about what the increment has to be here in order to take a distance of 3 and divide it into 6 equal parts. I think you can handle that. It's every half hour. So we'll have the calculator now set the table up to give us the values that we need. So we've already got the y equals in. I want to go to the table set. I want it to start at 0. And I want it to give me a y value every 0.5. And now when I go look at the table, I know the height of this trapezoid is 0. This one's at about 2.57, 3.94, and so on. Okay, I don't need those there. So to find the distance traveled, we're going to find the area of the trapezoids, and our shortcut is half of the first y value, which is 0, plus all of the middle y values, and then half of the last one, and the last one happens to be right here. Is that right? Did I type something wrong? Yep. Sorry about that. That's going to happen all the way through the year. I just looked. I keep going like I know what I'm doing, then occasionally I'll check back in my notes and see that I'm different. Forgot the plus sign. But it's all good. So these are wrong here, but my table set is still good. I just didn't have the equation typed in right. So this is not a 0. Oh, geez, my graph's a little bit different, isn't it? Sorry, guys. It happens. Right here to here. It's still good. Okay, sorry about that. I could have checked before. I had it covered up with a Post-it. All right, back to this, though. 0, 4, half of 4, plus, now all of the y values in the middle, 4.644. I'm still not matching. Oh, I only did 3 there. Okay. Okay, I'm good. Plus 4.9854. Let's go 4 places out. Throw a 2 on there. 4.8632. 4.3350. 3.6492, and then half of the last y value, half of 3.1284. All that times the height. The height of my trapezoids is a half. Because I went 0 to a half minute, a half to 1. Sorry I messed that up, guys. But anyway, now it's just crank it through the calculator. So 0.5 times 4 plus. That's the one thing about talking with no one in the room. If I make a mistake, there's no one there to let me know. So about 13 miles she went in her 3 hours. Oops. Right there, 13 miles. Okay, that's all I have. So what was new here was this new trapezoid rule. Definitely the calculator is a great tool to get comfortable with. Your assignment then on this section is going to be 1-4 Calc, page 21, problem 1, 3, 4, and 9, parts A and B. And that's it.